today. Yeah, I'm going to take the opportunity, I suppose, to talk to you about geophysics, how we use it to look for unseen geohazards. It's going to be a talk in two parts, really. First part is going to be the case for geophysics, and I'm sorry if you've heard us geophysicists kind of rant on about how useful we can be, but I'm going to try and demonstrate that through talking some of the applications we can do. I'll talk a little bit about geophysics in the sphere of 3D geoscience, where we are today with those kinds of technologies, talk about why we use geophysics, what it is. I won't go into specific methodologies. I want to talk more about how we use it within the context of digital data for ground investigations. And once we talk about what it is, we'll probably have to revisit why we do it again, just to make sure it's all firmly embedded. And then the main part of the talk will be talking about the use of 3D resistivity on a case study in a recent ground investigation overseen by Atkins. We'll round off with a little bit of a discussion about data cost versus data value before a summary at the end. So I'm going to make the case for geophysics. I'm not going to present the case against. Hopefully you can all come up with some good questions at the end that will formulate the case against, and we can have a good discussion about that. But hopefully this won't be the first time you're exposed to geophysics. You'll have had some indication of what it is previously. I noticed that some of the recent talks that have been held in the West Midlands Regional Group have had some geophysical content, which is really great. Where I think we are at the moment with 3D geoscience, and this is kind of my take on the potted history of sort of digital tools for understanding sites. On the top there, we've got the major developments in remote sensing from the last sort of 150 years, really, going way back to the sort of 1800s, where we use things like 3D stereoscopic imagery, which is still has its place in sort of ground investigation and reconnaissance today. And I think it's interesting that, you know, as sort of people who are interested in sites, we've had that sort of scope for looking for 3D information right the way back to that sort of early history of sort of photography. Of course, the explosion in high resolution aerial imagery, which came with sort of planes being flown over in the UK during sort of the world wars, before we moved to the launch of satellites for getting digital terrain maps, spot satellites in the late 80s, being able to provide us with 3D rasters for sites. And I think where we are today in terms of having that far more bespoke site-specific information that we can get from drone-based platforms, whether that's LiDAR, structure from motion, photogrammetry, all these things, which are really, I think, becoming almost bread and butter requirements for site investigations these days, just because of the lowering cost of drones and the sort of ease of use to be able to obtain these sorts of information for site investigation. And along the bottom there, you've got the kind of corresponding developments in geophysical investigations that happen along the same time. So right the way back from the early 1900s, the analog investigations using field equipment, moving forward to computational geophysics in the sort of 70s and 80s, where we're performing one-dimensional inversions. We'll touch on inversion later on, just in case that's something that people aren't familiar with. Before the real development in sort of engineering and environmental geophysics that took place in the mid-1990s. So this is the development of two-dimensional and three-dimensional inversion packages, which really saw the kind of advent of commercial geophysics, especially in the UK and America, and these technologies being able to be used by companies in their own right. And many of the companies we have in the UK at the moment who undertake geophysical investigations have been going for about 20, 30 years. So there's a good, strong industry in the UK in terms of geophysics, spanning back to the sort of developments in the middle 90s. And then finally, of course, more recently, we've been seeing developments in things like four-dimensional, so that's 3D and time-lapse applications of geophysics, mostly used for site monitoring, which really goes hand in hand with some of the developments that we see in 3D geoscience. And I think, from my perspective as a geophysicist, you know, it's been great to see these developments in digital data being acquired from drone platforms and satellites. And I think the fact that they're becoming embedded into how engineers think about sites is really great. But I don't think as geophysicists, we've done a fantastic job of really pushing the kind of information that we can offer in terms of understanding the subsurface, and bearing in mind that we really need to know about the subsurface when we are approaching a site investigation for the first time. I don't think we've been particularly good at sort of extolling the virtues and benefits of what geophysics can bring. The analogy I like to give is that it's the medical imaging analogy, which I'm sure many of you have heard. But if I was going to be going under brain surgery in the next few days, I would want the surgeon to have some sort of an idea of what's going on inside my head, using perhaps a sort of CAT scan technology or MRIs, rather than, say, a high resolution image of my face, which I don't think would be as useful for the purposes of doing that particular site investigation. So that's where I think we are. Excuse the sort of childish graphics on this, but it gets across a point, which is that when we're doing intrusive ground investigations, obviously we'd often have a budget. So we tend to use boreholes and intrusive investigations to understand what's going on in the site. And most of the time, we can characterize a site quite successfully using a sort of minimal amount of ground investigation intrusively. But obviously, if we want to build up a complete picture of what's going on the ground, we have to spend quite a lot of money to try and understand what's going on the site. And of course, that money is not infinite. We have to come to a point where we have to call it and say, well, we've got enough now to think that we, statistically have characterized that site. And of course, that's where we come in and perhaps make our interpretation of what's going on. And the question I'm going to be asking a lot throughout this presentation is the ground fully characterized by that investigation? And is the risk to design minimized? And I would argue that in this particular example I'm showing on the screen, it isn't. We've still got much or far greater areas of the ground which we don't have any information for compared to the areas that we do. So using geophysics, we can get some sort of very broad spatial understanding of what's going on in the ground. And we can do that using, for example, a resistivity meter, which is the technique I'm going to predominantly be talking about in this talk. And what that gives us is something of a very, very fuzzy picture. So we get this broad understanding, but the advantage is that we get that across the entirety of the site. And then from there, we need to try and narrow down our interpretations or reduce the uncertainties or the ambiguities that are associated with that data. So I think, and I think most geophysicists would agree with me, that we're not saying that we have the solution here, but what we are suggesting is perhaps that if we had some integrated approaches more often on our sites, where we took a bit of the budget that was available for ground investigation using the traditional intrusive techniques, and maybe couple that up with some of the investigation that we have, the investigation techniques we're able to do non-intrusively, we would get a much better understanding in terms of what's going on in the site at the site scale. So it's providing that holistic overview of what's going on the ground and reducing uncertainties. And in the context of geohazards, especially unseen geohazards, so we're going to be talking a bit about karst terrain in the case study later on, where we don't have that manifestation of some sort of hazard at the surface. This is a really powerful approach for trying to minimize the risk to our designs for whatever infrastructure might be built on our sites. So what is geophysics? I mean, at its absolute highest level, geophysical surveys are instruments that are deployed on the field. And we're talking predominantly about surface-based geophysics here. So this is usually either handheld, battery-operated equipment, which is taken to sites, deployed in some fashion. So there can be some techniques where you carry the equipment, you walk it across sites, and it has continuously acquiring data modes, which can then be generated to maps, or sometimes we deploy things like geophones and electrodes, and we try to get what are called tomograms or profiles through the ground. But we either have to artificially generate those signals, or we have to try and measure naturally occurring signals. And the signals that we're interested in are tied to some sort of property in the ground. So we can be looking at, for example, seismic velocity, which is related to the density of the ground, or we can be looking at measurements of resistivity, which is coupled with various parameters of the ground, including the clay content and also the degree of saturation as well. And the main benefits, as I've sort of touched on already, is that geophysics, are non-intrusive, so we don't have to break ground to get much of this data. At worst, we're having to put in some electrodes, maybe to 20, 25 centimeters depth, or some geophones, which have got spikes maybe of sort of 10 centimeters. It's inexpensive, and when I say inexpensive, that's really in relation to understanding the site spatially. So the amount of money that you have to spend to get the same volume that you would with an intrusive investigation is far, far less. So there's a cost saving there. And they're multidimensional. And the multidimensional aspect is really the thing that I'm interested in exploring with geophysics. I think it's where we as geophysicists are not, as I've said, not utilizing that capability enough. And the idea that we can get 3-dimensional models, 4-dimensional models if we're using time-lapse methods, I think is a really powerful tool for understanding what's going on the ground, and couples in really well with these developments we're seeing in remote sensing. In terms of limitations of geophysics, most methods have got limitations on their depth. So you tend to have decreasing resolution with depth. And often there's a trade-off between the resolution that you can acquire by getting data in the near surface. If you want to have high resolution surveys, you're normally going to have limited depth, so you won't get very deep. If you want to get deeper, you have to trade that off with shallower investigation, lower resolution investigation of the near surface. You can overcome that by using denser arrays or larger arrays in the cases of things like resistivity and seismics, but you're going to need more space to lay them out, and you're going to have to collect a lot more data to get that density. The other thing that's really important is they require a measurable contrast of some property in the ground. If there's no contrast there, we're not going to be able to detect something. Now, sometimes that's a good thing. We can use that to obviously say that we don't think there's anything in the ground which is going to cause a problem. So, for example, if we have a gravity survey and we have a pretty consistent gravity anomaly, we can say with some certainty that there's not anything within a critical depth of that instrument which is affecting the measurements that we're detecting. But generally speaking, if we're trying to identify things like discontinuities, or if we're trying to identify areas of heterogeneous ground, we need to have some sort of contrast in that property that we're trying to measure. So if, for example, we have some sort of backfilled cavity in the ground, but it's filled with a material which has got a very similar resistivity to the host material around it, we may not necessarily be able to detect that anomaly based on the fact they have similar geophysical properties. And that's why we tend to use multiple methods. So we generally try to encourage using more than one type of method so that we can target the different properties and sort of minimize those uncertainties associated with the sort of measurable contrast that we're looking for. And in terms of what we're actually measuring, the property that we measure using geophysics is rarely a direct measurement of the thing we actually want to know. So I've alluded that, for example, resistivity is sensitive to changes in saturation or changes in clay content, but it's not going to come back and say this is how wet your ground is, or this is how much clay there is in the ground. It will give you a relative contrast to the ground around it. And as I've also said there, the sensitivity of these measurements are not exclusive. So, for example, we could have very wet, very clay-rich ground, and it would be very difficult to differentiate between which of those is actually causing the change in, say, for example, a resistivity signature. I think one thing that's really overlooked is that, so we obviously understand from a physical perspective what it is we're measuring, but actually there are lots of errors that are introduced into geophysical surveys as well. And those errors can come from measurements in the field. They can be from poor practice, or they can be just from difficult ground conditions, but they can also be introduced in the modeling stage. Now, a lot of geophysical methods don't have a modeling stage. For example, if you're going out with an electromagnetic conductivity meter, and this is something like, normally looks like a ski, which you walk around on site, or you can tow it behind a vehicle, that's going to just be picking up measurements from the ground in terms of electromagnetic current, which is related to conductivity. And that generally is presented as a plot. And the only processing that needs is filtering of the data, but there's no modeling stage involved. But for the majority of methods where we're looking to actually get some sort of cross-section through the ground, or even some sort of volume, if we're using three-dimensional methods, we need to do an inversion. And an inversion is quite a complicated process. It's effectively the opposite of forward modeling. The analogy that I use is that if you had a bar magnet and you knew the size of that bar magnet and the magnetic intensity of that bar magnet, you would be able to forward model what the sort of magnetic bar field, sorry, the magnetic field would be around that. And the problem we've got with geophysics is that we're able to detect the magnetic field, but we need to back calculate the size and the magnetic intensity of that bar magnet. And of course, a very small, very strong magnet can produce a very similar sized magnetic field to a very large, very weakly magnetized magnet. And so we use this process of inversion, which is basically trying to fit our measured data to the model that we expect to the ground, and that is subject to errors, and it's something that is quite subtle and requires quite a lot of expertise to undertake. And so on that, I think it's important that with some of these methods where you're producing this model of the ground, that it is exactly that. It's a model. It's not a direct measurement in many cases. So whenever you see a seismic refraction survey, whenever you see an electrical resistivity tomography survey, as we're going to talk about later, what we're generally dealing with are models of the data rather than direct measurements themselves. So the phrase I think I need to get tattooed in my head when I talk to people in my office is that the map is not the territory in this. We're not actually taking direct measurements of the ground. We're producing models. And I think that's something that's not particularly well communicated by geophysicists. Now, it won't escape your attention that the list of benefits I've put there is quite significantly shorter than the list of limitations. And I think that's partly me just trying to be completely open and honest about what limitations exist. I think historically there's been, I know that from working in Atkins, I've only been with Atkins for 6 months. Previously, I worked at the BGS in research and before that as a contractor. But I know from talking to engineers that there have been lots of bad experiences with geophysics. Perhaps the expectations have been oversold, or people have promised that they can do things using particular pieces of equipment which just haven't come to fruition. So I think one of the things that I'm very keen to see is that as geophysicists, we're very open and honest about the limitations that we have. And that's not to say these things can't be useful. It's just to be very, very clear about where the limitations of these things lie. However, hopefully I won't put you off. And I think one thing to bear in mind is that, we're all as engineers having to come to terms with dealing with models more often. I think that's something that's really taken off in the last sort of 20 years of sort of geoscience. And of course, that you'll have heard this saying before, that all models are wrong and some are useful. And I think that's nowhere more true than in geophysics. and this follow-up, the approximate nature of the model must always be borne in mind. When we're talking about geophysical models, we are talking about approximations of the subsurface in the truest sense, but we're having to both make a model and interpret that. But as I say, hopefully you'll have an opportunity to show you how that can be used with some effect in this talk. So I said we'd sort of go back to visit why geophysics again. On the left there is a sort of plot which has been provided by Rod Edison-Fugro and my colleague Ed Cox at Atkins. And this is, I guess, in summary, what we're trying to do with geophysics. So you'll quite often hear people talk about a phased approach to ground investigation. And the same is true of geophysics. The amount of resource we have to investigate a site using geophysical methods is proportional to the amount of time and cost and effort that we have available to put into the ground. And obviously we have questions that we're asking ourselves as well with regards to geophysical surveys in terms of survey objectives, and budget and logistics playing into that as well, and the kind of flow diagram of how we might go about choosing methods to investigate the ground and the criteria with which we'd like to have to say whether the survey has been a success or not. What I'll do is I'll very briefly just go through these sorts of stages and explain the sorts of geophysical methods or approaches that we might find as we're going along this plot. So at the very top, we've got the kind of digital site screening approach. And this is like reconnaissance level geophysics, where you have a very, very large site. You maybe don't have a specific target in mind, but what you want to have is a broad understanding of the distribution of particular features on this site. The plot which I'm showing on the right there is actually an electromagnetic plot. It's very difficult to get the scale, but that's I think 5 or 6 very large fields. And what you've got there are a couple of metal pipelines which are crossing, so the obvious linear anomalies there. And then what's interesting is you can see the changes from blue to green, which is indicating the background geology on the site, and the areas of pink up in the sort of northeast corner there, indicating perhaps some made ground, perhaps some sort of anthropogenic metal content. And this is really just to provide a very broad overview of what's going on in the ground. It won't surprise you to hear that these things like electromagnetics, magnetics, ground penetrating radar are the ones that are most rapidly trying to be adopted for integration with drones, because if you can get these things up in the air and get them onto drones with a big enough payload, you can obviously acquire very rapid information from the site. I won't go into the debate on drones. It's sort of one that's raging amongst the geophysical community at the moment. Many people think it's entirely feasible and possible. Many people think it's never going to happen with the same data quality. But in principle, what we're trying to achieve here is a very broad understanding to get some sort of information from the ground. Electromagnetics rely on the transmission of an electromagnetic field and then receiving the electromagnetic current from the ground in the same instrument. And it gives us an idea of the ground conductivity. Conductivity is the inverse of resistivity. And really what we're looking for there are changes in the saturation of the ground, so the moisture content. Where we have more moisture or where the ground is more saturated, we tend to see lower resistivities and higher conductivities. Conversely, where we've got maybe more granular material, bigger pore spaces, perhaps air-filled, we tend to see higher resistivities or lower conductivities. Magnetics, fairly self-explanatory. With that, we're trying to pick up areas of ground which have got ferrous content. That's not just metal, so things like fired red brick obviously has a ferrous content as well, so we can map very subtle changes associated with that. And it's constantly used in archaeology because you can get incredibly sensitive readings that can tell you about things like historic hedge boundaries or burn pits, which are all associated with changes in the very subtle magnetic field affecting those. Ground penetrating radar, obviously one highly associated with sort of services and trying to identify utilities, but obviously has its place in trying to understand discontinuities in the ground, and normally seen as sort of 2D profiles across the ground. So they're generally speaking our digital site screening tools, where we can get very broad scale data sets to try and understand at the highest level what's going on with our ground conditions. Following on for that, we have, I alluded earlier on to the sort of 2-dimensional and 3-dimensional techniques at our disposal. So these are the cross-section type data, so the profiles, and I mentioned that normally these involve a modeling step. So there's a little bit more degree of understanding the data and having to really get to grips with what's going on, both in terms of your raw data from site, but also the modeling to produce the 2D tomograms. And generally speaking, the most popular methods we have is electrical resistivity tomography. So again, resistivity, the inverse of conductivity I mentioned earlier. So it can be incredibly useful to do a broad scale conductivity survey first, followed up by a resistivity survey, because you have data that can be related to each other in that case. And then seismic refraction tomography. This is using P waves and S waves to understand the velocity of the ground, which, as I mentioned earlier, is related to density. P waves generally sensitive to compressible ground, so you're looking at where you have areas of increase and decrease in density, and shear waves more sensitive to changes in ground stiffness and shear strength. And closely coupled to that, slightly different but related, is the multi-channel analysis of surface waves, which gives you an approximation of the shear wave velocity. And these can be used to build up these kinds of fence diagrams, which I'm sure you've all seen in previous talks and on your various encounters with geophysics historically. Incredibly useful. And I think perhaps coming really good for certain situations, but I think where we have to have a more detailed understanding of the site, there's an argument to say that we should be looking at gathering three-dimensional versions of these data sets, which is what the second part of my talk is going to be about. So I won't get too into that at this stage. We then have sort of in situ measurements of geophysics. So this is not particularly my speciality. I've always specialized in surface geophysics, but this is using downhole and crosshole wireline methods. So actually getting into boreholes, deploying equipment, or shooting seismics between boreholes to try and get a much better understanding of the actual lithological properties of strata as you go down the ground. And in there as well is microgravity, purely because it's a relatively slow technique that gives you quite a lot of information, but it takes a long time. So it's more in the kind of in situ camp. Even though it is a mapped technique, it just tends to fall on that time cost effort graph a bit further down. And this can be used to approximate kind of rock properties and elastic moduli, so very useful when looking for that sort of more granular level of detail with regards to the ground properties. And then finally on this graph, what we've got here is what the authors have called 3D geodata. And I think this is where my interest lies. This is basically using tomographic methods. So again, things like electrical resistivity and seismic refraction to get a three-dimensional image of the ground. So rather than thinking in terms of two-dimensional profiles, we're now looking at three-dimensional volumes of data. And most things you can do in 2D, you can do in 3D with the right setup, with varying degrees of effort. And I think my contention would be that beyond digital site screening, where we're just taking equipment out and walking around, we can do bad geophysics and we can do good geophysics. And bad geophysics is when we haven't specified the job properly, or perhaps we recommended the wrong types of methods, maybe too many methods as well, if we're just throwing things at it when we don't think they're going to work. Poor interpretation, importantly, no digital integration, so not actually bringing this data forward past the stage of just planning your next phase of investigation. All of that is not going to help reducing the uncertainty associated with investigating a site, but it is going to cost you time and effort and money. Meanwhile, good geophysics is when we obviously are able to have a think about the data we've got, build on those layers of actually having some understanding from the previous surveys, whether they be intrusive or non-intrusive, to really try and come up with appropriate specifications, identify suitable methods, where necessary, look for innovative processing and visualization techniques, and making sure that we're interpreting that data, with people who understand the ground conditions or have access to different sets of skills that we do. I think one thing that I'm really sort of pushing is trying to work with other people outside of geophysics to try and build up the skills of intercommunication and interdisciplinary thinking when it comes to these things, because it's our job to try and take the sting out of making things like the modeling processes easier, making the acquisition easier, making sure that things are done well. But the next step is then actually making sure it's useful. And that's something we'll talk about in the case study later on. And finally, as I sort of alluded to, is that in this particular graph, the 3D geodata approach, this kind of site-wide three-dimensional understanding, is right down there at the sort of time, cost, effort, and also in terms of reducing uncertainty. But I think actually we're at a stage now with particular sites and certain challenges where this can be introduced much sooner and with greater effect than it has done historically. And again, we'll go on to that in the case study, which is what we come to now. So I'm going to talk to you about the Welby tank 3D resistivity survey. Welby tank is a structure. It's literally a large overflow tank, which is being built on the field, which you can see in front of you at the moment. That's my colleague, Ed Cox, a fellow geophysicist at Atkins, doing a topographic survey. And if you've not seen a resistivity survey before, I'm afraid it is this boring. There's not much to it. But of course, we like boring, because boring means non-intrusive. It means not digging up the ground. It means not leaving things a mess. It means having a lower carbon footprint. It means having less cost. So boring for us is good. What we can see there in the far sort of back right of the picture is the resistivity unit, which is controlling the injection of current among the electrodes, which you can see on the screen there. And what we do is we inject that current between two pairs of electrodes, and we measure the arising potential difference across another pair. So we use 4 electrodes in that process across what's called a quadrupole. And depending on how far apart those electrodes are and where they are on the line, that dictates whereabouts in the ground the measurement's being taken. So if we have electrodes that are very far apart, we tend to see deeper into the ground. If we have electrodes that are very close together, we tend to see much shallower into the ground. And obviously we can move where the injection points are throughout the array to build up this two-dimensional picture of what's going on in the subsurface. And after about something like 800 to 1200 measurements, we end up with this two-dimensional cross-section of resistivity points, which we then take into our modeling software, and we try to produce a two-dimensional tomogram from that, which we can then build up into our 2D model, which is ready for interpretation. Now, with the 3D approach, there's 2 ways that you can do this. You can either put out lots and lots of electrodes, and you can inject currents at all different angles across the field by connecting up the cables. But when you've got a very large area, like this field, and this, I say large, this field's about 200 by 100 meters, we'll see in a map in a second, which is a relatively small area for a site investigation. But I think in terms of the density of data that we're requiring, it's quite a large area. It's impractical to actually hook up I think what would be hundreds of electrodes to do the measurements at the same time. A two-dimensional line like this takes about an hour to run. So if you're trying to hook up 15 lines together and then do all the combinations of electrode injection points, it would be longer than you can do in a working day. So what we do instead is we acquire all the data separately as parallel two-dimensional lines, and then we can take that into a three-dimensional inversion software as one whole data set. And the software is able to then look at the corresponding measurements either side of an individual 2D line to make assumptions about, or just overcome assumptions, I should say, about where the current is flowing in the ground. And this has big benefits, not just in terms of the coverage you can achieve, but also in terms of reducing what we call 3D effects. So a good example of that would be if Ed was holding a metal pole here instead of a sort of instead of a fiberglass detail pole, that would be a conductor in the ground. And if he was standing a few meters away from that line and we inject a current, there's every possibility the current might flow through that pole, or at least be directed towards it, because it's got more conductive, it's a more conductive body in the ground. And the problem with our modeling software in 2D is it makes the assumption that everything is beneath the line. So although the current is actually a three-dimensional phenomena, the two-dimensional inversion algorithm will only pick up, or it will assume that everything that's being picked up is directly beneath the electrodes. And we know that obviously that's not true, because current flows wherever it's going to go in 3 dimensions. So by using a three-dimensional algorithm, we can overcome some of these problems. And interestingly, of course, that applies to any conductive body. So for example, if we have a sinkhole that's full of clay that might be slightly more conductive, that's just off of our line, and the current's going to be directed through that, it means that we can start to actually localize that in 3 dimensions rather than making the assumption it's directly beneath our line. I should have said that if anyone's got any questions, I'm very happy to take them at this point, because I realize we're going through quite a lot of sort of physics-based stuff. Otherwise, feel free to ask them at the end, or just contact me afterwards. I'm very happy to explain anything. So the site itself is situated on the Upper Lincolnshire limestone, which is known for having several hazards, including karst. So we've got potential presence of dissolution, sinkholes, voids associated with sinkholes or backfilled sinkholes. But we've also got an eroded bedrock topography as well. And what's happened in this particular part of the world is we've got differential deposits of glaciofluvial material. So basically we've got areas where we've got very shallow, potentially quite competent bedrock, and then these scoured channels which are filled with glaciofluvial material, which is very clay rich. And of course, if you're trying to put a tank, and this is the largest tank that's being built as part of the Strategic Pipeline Alliance, which is being run by Anglian Water, you want to make sure that that is basically all sited on the same material to avoid the risk of differential settlement. And interestingly, because it's an overflow tank as well, one of the things you want to consider is if there has to be an emergency release of water, that you're not pumping that water into, say, a sinkhole which is situated just off the edge of the tank, which may then be rapidly dissolved by the vast volumes. I should have put in the actual amount of water that's discharged from this thing in emergency, but it's an extremely high flow rate. So the potential for disturbing ground that may already be slightly unstable is quite high. So they're the 2 main things we're looking for. We want to understand if there's a risk of dissolution and karst. We also want to understand what the thicknesses of the glaciofluvial material overlying the site are. So on the right there, we've basically got 2 fields which are under investigation for this project. The pink areas are the superficial deposits as mapped by the BGS. So that's just the available information that was there before the project. And then throughout the project, what's been done is there's been a multi-phase, multi-method approach to the ground investigation. So phase 1 was a reconnaissance geophysical survey, so using some of those digital site screening tools that I mentioned earlier, and that basically consisted of an electromagnetic conductivity survey. So again, this is walking or driving up and down with an electromagnetic conductivity meter and looking at the change in conductivity in plan view. And then they followed that up with some very broadly spaced resistivity lines, which is what the red lines are on the map there on the right. That was followed up by some intrusive investigation. Now, they actually did some intrusive investigation across the entirety of the site, but it was decided at this stage that they would just focus on the field to the east because there was shown to be too much glacial fluvial material in the west. So although there were more boreholes drilled in this part, we're going to focus on the eastern part of the site as we move down through these different levels. And at that point, it was suggested that maybe enough had been done on the site, and perhaps that was good enough for the understanding. And we sort of said, well, actually, no, we think there's quite a lot of ground here which is still not understood. So we suggest doing a 3D resistivity survey, and that's what we did. So just quickly go through those phases and a bit more information. So I mentioned that the first thing that was done was a ground conductivity map using an electromagnetic conductivity meter, and this was done by Teradat, a sort of geophysical specialist contractor based in Cardiff, who I used to work for, and a really great understanding what there needs to be done to get the broad scale understanding of the site. And so we can see here that where we've got these areas are dark blue, which broadly correspond to the areas that were mapped by the BGS as being glacial fluvial material. That shows us where we have these areas of clay-rich glacial fluvial deposits sitting on the site. But obviously, being a plan view, it doesn't tell us much about the thickness of those. So it's decided that they would follow up using electrical resistivity tomography. So they did several two-dimensional lines as a sort of fence diagram, and this is us looking over there to that northwest of the field there, where we had the low conductivity meter readings, and we can see that we've got lots of areas of blue here. So in this case, blue means low resistivity, which is the equivalent of high conductivity. So we can see that actually, we probably got varying thicknesses of glacial fluvial material present on the site. There's also some interesting variations in this as well. We can see that although we've got some what look like fairly uniform strata, there's definitely areas at this site which have got some changes in the near surface resistivity, and that's great. We've got lots of data here. We can start making some interpretations on that. But in terms of our understanding of the site, the question that I would ask is, is the ground fully characterized, and is the risk design minimized? And I think the answer would probably be no at this stage. The reason for that is because if we're interested in understanding what the thicknesses of superficial deposits are for a very large tank, which could easily sit within the area which has not got any data here, and we're also trying to understand what the presence of things like potential sinkholes of dissolution are, which may only happen on the order of a few meters. This data isn't actually giving us enough information about the site to be able to confidently say, no, we don't understand, we fully understand what's going on in terms of the hazards. So I said the next phase was to go and do some intrusive investigation. Again, just focusing on the field to the east here. So 8 boreholes were drilled in total that fall within this field to the east. And the boreholes logged a range of sort of superficial gravels and various other clay-rich materials down to about sort of 2 to 3 meters. And then underneath that, limestone in various sort of states. So in the south here, dark blue represents an area of very strong limestone as logged, and then varying degrees of strong and medium limestone before we get to the north, and you've got sort of much weaker and medium limestones there. So again, you might very reasonably say, well, it looks like towards the south of the site, we've got far more competent bedrock, but actually most of it, the stuff we're picking up here is absolutely fine. We don't seem to have significant thicknesses of glacial fluvial material, and as long as we avoid the northern part of the site, we're probably okay. Again, that question, is the ground fully characterized? Is the risk to design minimized? We argued no, and we suggested that should go back and get a bit more data to try and actually understand the site in 3 dimensions. So at this point, what we've done is we've gone from having these 2 fields, we've zoomed down by using a range of techniques, including reconnaissance geophysics and some intrusive information, to this area here, which is now, SPA have already made the decision that with this field, which is developed rather than the western field. So this stage, this is where we're going to design our 3-dimensional ERT profile. So you can see the lines here, which are slightly longer and shifted to the south. They're actually the original lines that were undertaken by Teradat. So we've reused that data in this acquisition, and that reduces the amount of data we need by about 15%. So we're able to build on the data we've already had, and that can be included in the 3D model. It's not visible on the aerial image here, but there was actually a large pond excavated in this corner of the field. So we had to shift these lines slightly south. And we did another line up here just to try and make sure we were getting the depths towards the north, because we knew from the boreholes that there was some interesting variations in the lithology there. So we've gone from having 50 meter spaced two-dimensional electrical resistivity tomography profiles down to having about 8.5 meter separated profiles. And crucially, rather than having two individual measurements 50 meters apart, we can now take all this data and we can process it into one three-dimensional block. It took about 4 days to acquire in the field. We actually did this in-house, so we hired in the equipment and used our expertise to go and get this and process it. And I think important to note that what we've got here is basically a 500,000 meters cube model of this site now. So we're looking at about 200 meters by 100 meters and about 20 meters depth. And so when we run this through the inversion algorithm, this is just now going to cycle down at half-meter intervals down through the ground. And I think what's really interesting is that the four boreholes, which are represented here by these four dark squares, which are the same ones that you saw on the last slide, actually the three in the south, just by complete coincidence, have drilled into what I would say are the resistivity maxima of this model. So where you have the highest resistivities at depth is where those boreholes are. And actually, if you look at this area in between those boreholes, we've got these yellow and orange values here, which is pretty low resistivities for the site, and that means that there is some change in the ground character there. As we get to the surface, we can see this dark blue we think is the influence of seepage from that pond, which was water filled, possibly flowing through an existing channel or having just found a preferential pathway in the near surface, and that's great. So fantastic, we've made a very pretty picture of lots of different colors, but what does it mean? And for this project, we actually had the opportunity to sit down with the design engineers for the tank, and we had two options at this stage. We could sort of say to them, well, we are the geophysicists and we are the experts, and therefore this is what you should do. Or we decided to take a slightly different approach, and we thought we'll take them along for the ride. We'll actually try and talk through with them why we've made the interpretation that we have, what we think is going on with the ground here, and basically, explain to them rather than tell them. And so what we did is this isn't a particularly complicated step in the analysis, but I think it is something that's not done as routinely as it should be. So just for the moment, we'll ignore the blue and the red lines here on the left, and we'll just focus on the yellow, purple, green, and sort of dark red lines on the right there. So what we've done is they are effectively our resistivity depth profiles at the locations of the boreholes. So we've taken from the 3D model, we've taken the resistivity values going down at the same point of the boreholes, and then just using those different shapes, for each point in the model, we've assigned there whether it is weak limestone, medium limestone, or strong limestone. And what we were trying to prove is that conventional resistivity theory would tell you that where you have more competent ground, where you've got less clay-rich material because it's less fractured or it has less water in it, you're going to have higher resistivities. Something I should have mentioned is that the groundwater table, we believe for this site, is well below the 20 meters that we're looking into the ground. So we're kind of removing groundwater as one of the assumptions that we would normally make about the ground. So we're assuming that the variation in resistivity here is either associated with perched water, or it's to do with the change in clay content or fracturing of the solution states. There's still several things that we're possibly indicating as the sort of cause of our change of resistivity. But I think what's really interesting is that particularly where we've got lots of strong limestone logged, which is at the deeper boreholes here, they're generally the stronger the medium and stronger limestones tend to fall where you have higher resistivities. Interestingly, when you've got very, very shallow readings, there isn't so much of a correlation. So we had to make a couple of assumptions in our analysis. And what we said was, okay, we're going to assume that for the borehole, which was in the north, which has got the weakest limestones recorded, that there's some sort of statistical significance between the resistivity values at that point and the rest of the site. And what we mean by that is that basically where we're seeing weak limestones that are showing low resistivity, that is a relationship that holds true across the site. So that's the first major assumption we're making. And then the second major assumption we're making, because we've got this rather complicated picture at sort of 6 meters and above, and we can see a much clearer image in terms of relationships from below 6 meters, what we're going to say is that, okay, well, if the limestone between 6 and 10 meters is weak, then we're going to make the assumption limestone above it is weak because we're looking for dissolution, and we assume that these are top-down processes coming from infiltration of water, which I know is not going to be true in every case. Where we've got ground-based or rainfall-based dissolution, that might be the case, but perhaps not for fracturing or cave formation. Now, we have screened the data for cave formation already because if you had an airfill cave and resistivity, it would present as incredibly high values, talking tens of thousands of ohm meters, and the maximum we're seeing across this model is sort of more in the 1200 ohm meters, so a good order of magnitude less than we might expect if we had open voids in the ground. Sorry, excuse me 1 second. Okay, and then we said, so using conventional resistivity theory, we would understand that actually, if you've got weaker limestone occurring at low resistivity values, we can probably extend that area to actually being anything from about 420, 450 ohm meters down to 0, because it's incredibly unlikely, or at least we couldn't think of a physical scenario where you would have competent limestone that would have resistivities higher than anything you would see as the weakest values recorded on site. And again, because we're using this assumption that the limestone above will be weak, we can also extend that to depth as well. So effectively saying anything that has got low resistivity values at depth is a risk of having some sort of change in its structure or nature, which may be associated with dissolutioning, perhaps increased fracturing, something which is increasing the amount of clay content in the ground there. So then what we did is we went back and we said, well, look, there's two features on this plot, which we've got, the 3D volume, which we think are particularly interesting because they present as these areas of localized low resistivity, which continues down depth. And we basically plotted those out as if they were virtual boreholes, and that's what the resistivity profile 1 and 2, the sort of red and blue, are here. And really just making the point that actually in your 3D volume of resistivity, we've got areas which are showing at much lower resistivities than even the weakest limestone that's been recorded in your boreholes so far. So basically, the boreholes have not picked out the worst case scenario in terms of ground conditions for this model. So using this, we've now got a rough idea of some of the kinds of thresholds that we can understand for the site, and we can then start to say, we think in terms of risk of dissolution or in terms of change of the ground condition, which may affect the design of your infrastructure. These are the areas where you have resistivity, which is much lower at depth, and we think therefore you have a higher risk of dissolution. And this is the risk map that we're able to make from that in terms of 3 dimensions. So in light colors in the background there, we've got the raw resistivity data, and then this kind of voxel model over the top there is showing where you've got these higher risk zones. Is the ground fully characterized? Is the risk design minimized? Well, there's probably more you can do, but everything's got, all good things must come to an end. So at this point, we presented the client with this, and actually they said, well, no, we need to go back and drill some more things. So I'll show this video because this sums up quite neatly what we're able to do with the ground in this, with the data, sorry. So zooming into our site here, we've got the 4 boreholes that were initially drilled. Again, these all show areas of increasingly strong limestone to the south, and then just dropped over the top of this is our 3-dimensional model. And what we can do is, I mentioned that we had a sort of thickness of superficial deposits. We can basically strip that back. So we're just looking at what is effectively the bedrock surface here. So about 2.8 meters below the ground. And we can see quite clearly here where these 3 boreholes just happen to have intersected what we think is probably the stronger material on the site here. As we play through this, I mentioned obviously we did that integrated analysis, and we can start to look at where we think the higher risk zones are. Of course, conversely, we can look at where the lower risk zones are as well. So this is where we've got higher resistivities at surface. And I think when we overlay these two things together, this is where we can start to see some interesting features coming in. So we have this area here, which has got what we would say is a relatively low risk zone, but right in the middle in this kind of concentric ring, we've got something which is extending down through the ground, which meets our criteria for being something which may be risk of dissolution. Obviously, a much more varied picture towards the north, where we know we've got the weaker limestones which are present at the borehole. And I mentioned there's a pond here, which we think is probably seeping water out into perhaps a sort of clay-rich channel. And if you remember going back to the BGS mapping, we actually had areas of clay-rich deposits mapped in this area of the site. So the real advantage of this is that we can obviously give this over to the design engineers in 3 dimensions and say, well, look, you've got a footprint that you need to put your tank on, and you can now have this 3-dimensional model, and you can start playing around with simulating where your tank might go, which bits of ground it's going to go on, and so forth. Of course, the next stage after this actually was they said that, there's enough in here that we'd like to go back and do some more ground investigation. So Following the 3D resistivity, the site was actually drilled again. They've just completed drilling, I think, 5 more boreholes on the site, and we are yet to get that data. It's a shame we didn't have it for this presentation, but you'll know if it's worked or not, because I'll either have a job in a month or I won't. So I'm going to sort of finish off really just by talking a little bit about data cost versus data value. The initial ground investigation, and this is the intrusive ground investigation now. So this isn't counting any of the reconnaissance geophysics that was done at the beginning of the ground investigation. So the 4 boreholes that were drilled, what we'll do is we'll try and think of this in terms of cost of borehole equivalent. So I'm not going to put values to it, but this is just talking relatively in terms of cost per borehole. Interestingly, when you drill 4 boreholes onto the site down to 20 meters, and you look at actually the volume of data you get for that, it comes out to about 1 meter cubed. Now that's gold standard data. That's actually having something from the ground that you can log. You can see the fabric of the mineralogy, everything you need to know about it. But it is a meter cubed, so that's what we're dealing with in terms of coverage. And the geophysical survey, which cost about half of the cost of the 4 boreholes that were drilled, gave us 500 meter cubes of data. And interestingly, off the back of that, it was 5 more targets for investigation were identified, which you get about another 1.25 meters cubed of data. So bringing you up to about 2.25 meters cubed of again, gold standard, engineer log data from which to interpret your site. So I think the point I'm trying to make is that in terms of value, I would never make the argument that 1 meter cubed of logged core is equivalent to 1 meter cubed of resistivity data. There's no way that if you went out and tried to characterize the site using just a few meters cubed of resistivity data, it's going to tell you anything useful whatsoever. But I think there is an interesting point on cost here, which is that actually, when you look in terms of coverage, in terms of the volume of information you're getting from the resistivity survey, 1 meter cubed of resistivity data is actually 1 million times cheaper than 1 meter cubed of log core. And this really goes back to the point I was making at the beginning of this talk, which is that I think the integrated approach to doing these ground investigations, using the geophysics to have the holistic spatial understanding of the ground, supplementing that with the observations you get from the ground investigation data is really the best way to do it. And that actually, had we thought about things a little bit differently, we might have been able to do the 3D resistivity survey first and have those targets which would have been brought up in the ground investigation, and we could have perhaps saved, drilled a third less boreholes, which would have paid for the resistivity survey and saved some money on the project as well. So with that, just some very, very brief conclusions. If anything, I want people to take away from this that 3D geophysical models have a really important role to play in the right types of projects for understanding unseen ground hazards. So where we don't have obvious manifestations of hazards at the surface, being able to get this 3-dimensional site-wide holistic data, it is a really good way of trying to broadly understand what the changes in character of the site are and understanding heterogeneity associated with those geohazards. I think where we can take this data and combine it with integrated data, so sources of intrusive or remote sensing or other forms of observations, that just gives us the multiple lines of evidence that we need to really understand what the potential of geohazard prevalence is across the site. And the one take-home message I want everyone to really consider is that geophysics, whatever form it is, it's an important source of digital dynamic data. And I think geophysics has been used in the past primarily to plan lots of investigations. So where you're going to put your boreholes, what you're going to do next, and quite often is dropped at that point of the investigation. And I hope today we can show that, actually having geophysics as a 3-dimensional digital deliverable, which can be used in some sort of modeling package taken forward along with the investigations you get from intrusive approaches, means that you have a product there which can go with the lifetime of the project and not just be used as the reconnaissance phase and then dropped. And that's certainly where I'd like to see geophysics going in the next few years. So I'd just like to acknowledge the people who are part of the Strategic Pipeline Alliance who helped this work to be done, including my colleagues Ed Cox and Chloe Rushworth from Atkins, who helped it to happen. And yeah, with that, just like to say thank you very much for listening. And if anyone's got any questions now or later, please get in touch. We'll be very happy to answer them.
Thanks, Jim, for giving that talk. It sounds like you've set yourself up for part 2 when you've got that other data.
It does, doesn't it?
I'll just stop the record in a second.